Okay, we started. Sorry about that.
Yeah, you get a nastygram if you don't do a recording.
Okay.
Okay, so you're going to have a coupler. Now, if the coupler is glued into the fiberglass section, I mean, the main then has to come out through the coupler.
Yes.
Okay,
We will be using shear pins. We're going to be using nylon screws. And on the top end, the separation is going to be using CO2 canisters. And at the bottom, we'll be using black powder.
okay, so you're using CO2 for the booster drogue.
Yes.
Okay.
We also made a design modification. So, and one of your comments was that the drogue should not be deployed at separation because it's going to be going at Mach 1 almost, well, actually Mach 1.3 something. So what we did is that we will have, so one of the couplers, we have extra piece of it. So it will slide inside and it will be closed with more shear pins. That way the drogue will only deploy once it gets to apogee, even when they separate. So the the drogue will not deploy at separation at high speed.
Yeah, that would be a bad thing, but I will, hopefully you can piece together the components to show the interstage coupler, or we can look at a drawing so that we can see how the pieces will be laid out.
Yeah, for sure.
One suggestion that you might consider with the approach that you're using
Mm.
uh, is to instead glue the coupler tube into the top of the carbon tube.
Okay.
I'll just give you a term that you can search on, and the term it's called a zipperless coupler.
Zipperless coupler. Okay.
And basically just go ahead and look for that. If you want to, I did a Narcon presentation in 2021. Uh,
Hmm.
and it talked about zipperless couplers and why they're good things and why you might want to use them.
Okay.
Uh, and since you don't have it installed yet, because the concern would be that you're going to be putting out a main and now it has to go through a size reduction. Okay,
Yes.
it has to go through the coupler in order to get out.
Yes.
And it's actually a better practice to have the coupler in the other tube anyway. So if you want to explore that and maybe look at that as an option, you could do that still.
Okay. We will do that.
Okay, and that was the Narcon 2021, and that's available
Okay.
on
Narcon
YouTube.
2021 Zippler coupler. Okay. Zipless coupler. Okay. Yeah. Someone wrote it down.
Okay,
Uh, for the second stage, I'm just gonna move here. So the second stage motor tube is a bit smaller. We already did the tip-to-tip carbon fiber layup. We still haven't sanded it down. So it is a little bit shorter because the motor is L910. L910 is also smaller in diameter. That's why we have an inner tube. So the inner tube right now has a centering ring, and it will slide inside. And the centering ring will eventually stop at the fin tabs. So those fins have tabs inside. See, so it will rest at the fin tabs, and after it's inside, we will insert a second centering ring from the bottom, also to rest against the fin tabs, and we will epoxy it there. Of course, a similar approach. We use epoxy mixed with milled carbon fiber and Cabasil just to make sure everything is strong. Also, because this is going to be going higher in altitude, we're going to drill pressure relief holes. That way, any pressure difference will not cause any issues. Uh, and again, it's going to be a similar setup to the first stage. We will have a coupler, a bulkhead, and then the coupler, and then the recovery section, which is also another carbon fiberglass tube. with a similar approach, pretty much. You mentioned sorry, do you have any questions before I continue?
Yeah, let me ask a little bit about, okay, now that's going to be your motor is going to fit in that tube,
Yes,
and you're going to lower that down, and it's going to sit on the fin tab, and then you're going to put another centering ring
from the
in
bottom.
from the bottom.
Yes.
And so how much room is there going, and maybe pick the rocket up with the fins on it and hold it sideways so that
Yeah.
yeah, so, and then you're going to have an interstage coupler that slides into the bottom then?
Yes, correct.
That
And
goes,
it will have it will be 4 inches because the fin tabs they don't go from the very back to the very bottom. There's actually like a half an inch, so the thickness here is around 4 inches.
okay. And so when you transfer the thrust with this design,
Hmm.
you are going to, well, one thing you're going to be doing, well, let's see.
This design we have used it before. Actually, if you see here, this is our rocket last year. It used the exact same diameter for outside and the exact same diameter for the motor. And we used the same approach with a inner tube with centering rigs on top of the tabs and under the tabs. And it just works fine. Like we've tested that for a couple of years. It's not like a new approach that we are trying.
Okay. The only comment I want to make is that when you assemble all of this, since it's the thrust transfer location, you want to be very particular about how you do the epoxying.
Yes.
And the key step that many teams or many Rocketeers don't do
Hmm.
is, they'll go ahead and they'll sand the surface that's going to be glued. Uh,
Hmm.
and then they'll clean off the surface that's going to be glued, but then they just put in the tube and put in the fillets. And the key step that really makes the bond good uh, is it's like you would take your finger with the glove on it, and you would rub the epoxy into the surface that you're going to be gluing. I call it buttering the surface.
Yes.
And it gets the epoxy down into the little scratches and the little grooves and so forth
Yes.
on the surfaces that you're gluing. And then the bond will hold. If you don't do that, it doesn't matter how much epoxy you put in.
Yes.
It will let go on you at some force. So if you
Yes.
do that buttering process on both the motor tube and the inside of the airframe, you'll have a better chance of success that bond will hold.
Yes, of course. I also want to add that our centering, if you can see, it has like little circular cuts. That way,
Uh-huh.
the epoxy will be able to go from both on top and bottom. So it's going to create like kind of like a clamp that goes around it.
Okay.
Yeah.
All right. Maybe another opportunity for a zipperless coupler too, by the way, if it's not in there yet.
Okay. No, it's not in there yet. The couplers will be delivered like in 2 weeks, so we have time to check the changes.
Okay.
So the next thing, so our payload section, we have acrylic tubes. We just purchased them the other day. So they are acrylic tubes, so they are clear. We did compression testing on them to make sure that they can withstand all the stress that we will encounter. Sorry, they are still new, so I haven't opened them yet. Our camera will go inside and it will pretty much be rotating against the rocket roll. So it will have a stable-ish video. We are using one of DJI live streaming cameras, so it will have a range of like 20 kilometers. We are trying to actually participate in the live video challenge, so that's one of the things that we will try. Uh, those actually have slightly larger diameter. So our outer diameter on the rocket is 4.11 inches. Those are 4.25, and that's why after we put them in with the couplers and everything, we're gonna make a little fillet with Bondo, so it doesn't have a shockwave. Although I did simulate it with shockwaves without any fillets on Ansys, like in CFD, in the Fluent, sorry. And it would still withstand everything, but of course we don't want to have like a sudden change in diameter, so we're just gonna fill it that. Or actually chamfer it.
Are you using one clear section or two?
Only one. But we have a second one just in case something broke or
Okay, and that's going to go, and that is your payload?
yes. So the actual payload is this one here. This is just a prototype so far, but there's basically a servo, and there will be like more sensors that will measure the rocket roll, and it will be rotating opposite to that. So the camera will not be like going crazy with the rocket.
Okay,
The bulkheads for that, so we have two sets of bulkheads actually. Two are aluminum and two are steel. So based on how much it's gonna weigh at the end, we might go with steel if it doesn't reach the 8.8 pound. But if it does, we're just gonna switch to aluminum because so we don't want to go overweight pretty much.
Can I interrupt and just ask a question?
Yeah, of course.
I want to go back to your interstage coupler.
Yeah.
Is your coupler, I thought you said your coupler would be attached to your sustainer. Is that correct?
Yes.
So the coupler's glued into the sustainer and drops into the booster.
Yes.
So then the motor goes to the bottom of the coupler. Is that correct?
Yes. So this will actually have 1 inch going outside, and when the coupler goes, the coupler will even be extending a little bit more. So the nozzle is actually going to be slightly inside the coupler.
So how long is that coupler into your booster tube? Is it the full 4 inches or is it less than that?
Oh no, it's full 4 in both ends, like 4 here and 4 in the booster.
So your motor's basically sitting 4 inches farther down than the bottom of the tube.
No, not really, because
Well, the end of the nozzle, like
yeah, the end of the nozzle is around 2 inches inside because this inner tube actually protrudes out a little bit from here. So it's gonna be 4 inches in total. So 4 here and 4 here. So it's gonna be kind of like in the middle.
so.
Once we open the open rocket, this might be easier to see.
I'm just concerned your nozzle's gonna. I guess it doesn't really matter, but your nozzle's gonna torch the tube. Like your
Uh,
thrust is gonna torch the tube, unless your
it-
nozzle's at the bottom.
yeah,
And then you're gonna have a vacuum. So
yeah, it is something that we were thinking about. But to be honest, this is our first experimental two-stage, so we're not too particular about reusability right now.
yeah, but well, Jim might have a more of an opinion than I do, but I mean, you're potentially dropping burning pieces of carbon off the bottom of the rocket in the desert. So it's a question of whether Ezra is comfortable with that. That's why I'm asking.
well,
Uh,
I thought that the interstage coupler was going to slide into the bottom of the rocket and would not be glued to the sustainer, but would be glued to the booster. Did I misunderstand that?
Yeah, it's glued to the booster, but the motor's inside the coupler and it's recessed up into the coupler. So their thrust is going to be inside the coupler. Maybe not very far, but it's still inside
yeah,
the coupler.
it's around 2 inches.
Okay.
I-
Maybe position the coupler where it will actually be, or let's not call it the coupler, let's call it the motor tube. Position the motor tube where it will actually go to.
So if I understood what they described, Jim, the motor tube is above the fins and there's no tube over the motor
No, I
below
don't think
that.
that's
Is
what,
that right?
I don't think that's it.
Here, let him show us.
Okay, I'm gonna insert it. Just give me a second. I hope it doesn't need any hammering because last time it was a little bit.
It's still tight, is it?
Yeah, it's supposed to be tight. So, uh,
I'm mostly asking because normally the coupler would be on the booster, not on the sustainer, I would
that is
imagine.
correct. When we needed, originally that was the idea, but since we don't want to deploy the drogue directly at separation, we decided to push the coupler to the sustainer. From there, sorry, and we're gonna have another piece of coupler. A short, like it's not really a coupler. We're gonna have an inner tube in the first stage with like a bulkhead on top that will that way it will contain the drogue and it will only deploy once we get to the apogee. Sorry, it's a bit hard to push right now unless like I want to like hammer it. But basically, sorry, thank you. Basically, as you can see, they are now inside each other. So it's not all the way through. But when it gets all the way through, it will be an inch outside here.
Okay.
Yeah. So
Which is where the motor will go then, right?
yeah,
Right.
and so the motor also has like half an inch, and the nozzle is also a little bit there. So the very end of the nozzle, the exit like area is gonna be 2 inches away from here. With 4-inch coupler, it's gonna be 2 inch inside the coupler.
So the nozzle's inside the coupler.
Yeah, by 2 inches.
Yes, that's what I thought I understood.
Yes, correct.
Okay, so do you have the interstage coupler yet, or is that something you're still waiting on?
No, we're still waiting on it. It's gonna be delivered like in a week or two, probably 2 weeks.
Okay, so, and are you going to put a switch band on that?
Sorry, a switch?
A switch band?
What do you mean by switch band?
Well, okay, if you don't know, then that's not what you're planning, so.
Oh yeah, I guess.
So you're gonna have the coupler then, it's gonna be how long?
Well, it's gonna be 8 inches in total, so
Oh,
4 inches.
okay,
Yeah, and 4
so
inches
you're
long.
gonna have, okay, so 4 inches is gonna go in the airframe,
Yes,
and then you're gonna have, 4 inches sticking out,
yes,
and the motor's gonna go 2 inches down into that lower 4 inches.
correct.
Okay, and is there gonna be a bulkhead then in the coupler, or?
Like here, no, where there isn't gonna be.
Okay, so then that coupler then is going to go into your upper airframe?
Like here, yes.
No, I mean, into the upper airframe for the
Into
booster.
the upper side of the booster. Yeah.
Yes, correct.
Okay, and what's the next component that comes along?
In
You're
the
gonna
first,
have the coupler, and it's gonna be 4 inches into the,
yeah,
um,
and then there's gonna be the shroud that goes around the drogue, which is attached using shear pins. So the parachute will not come out until it gets to the apogee.
okay, but there's no bulkhead above the drogue. It's just going to,
Well, it's not. I mean, you can call it a bulkhead, but it's pretty much like a cylinder with closed top. That is like kind of a shroud that goes on top of it.
okay, like almost like a piston perhaps?
Yes.
Yes.
Okay, now, I think you said you were gonna use CO2 to do the stage separation?
No, the CO2 is to deploy the drogue, and the stage separation, we're actually going to be using the thrust from the second stage to push the first stage
They're
off.
gonna
It's going
hot
to be hot.
stage.
Yeah, exactly.
Okay, so you're going to hot stage against this piston
Yes.
that is over the drogue.
Yes.
I presume you've got something below the piston to stop the thrust from pushing it down?
I mean, it's going to be long enough that it will touch the bulkhead that is even under it.
Okay.
Yeah.
I see. I understand.
Yeah.
I was most concerned about the fact that the nozzle was inside the coupler.
Hmm. No, I see what you mean. We actually thought about that. We kind of looked at what is the temperature that the epoxy and fiberglass will start burning at. It's definitely going to start burning. Like we are aware of that. It's just that for us, it wasn't a concern because, again, this is a very experimental rocket for us. I know we're probably going to lose some points on not being able to like refly again. Like it's not going to be reusable on the spot. But yeah. But in terms of safety or something dropping from the sky, I don't know to what degree that could be a concern or not, because I'm pretty sure if they were to burn, they're just gonna burn into dust immediately. But I don't know, to be honest, I didn't think of that aspect of it.
Okay, so let me continue to try to clarify this for me.
Hmm.
So is the interstage coupler tube,
Hmm.
uh, that's going to slide into the bottom of the sustainer, right?
Yes.
Is it going to come out when you stage?
No, it's gonna remain on the sustainer.
Okay,
Is
so
it's gonna be
okay.
glued.
All right, so the motor is going to be inside that coupler by a couple of inches.
Yeah, by 2 inches.
Okay. And so then that coupler then is going to, so the booster is going to fit over the top of that. And then you said that the drogue will be in there, but you'll have like a piston that covers the drogue.
Yes.
Okay, and that piston will then be ejected for deployment.
Once we get to apogee.
Okay.
Yeah, we might also want a couple of them in case we mess them up. I'm gonna grab like this.
Sorry?
Yeah.
Sorry, I can't hear you. I think they might have like forgot their mic unmuted. Okay. Should I go to the next step, or is there more concerns we need to discuss about this?
Well, I'm wondering, okay, I'm going to try to envision, so that from the point of view of the booster, then the booster is going to slide over that coupler by 4 inches. And
Yes.
so so there's going to be, and is the piston then is going to be directly in contact with the interstage coupler?
Uh, it's got no, it's gonna be under it. So the tube of the booster, it's gonna be sliding on top of it, and then at the end of the like by 4 inches, the piston will come. So like the piston is gonna be the same diameter as the coupler.
Right. Is there, okay, is there, what I'm trying to visualize is how long is how long is the coupler above the top of the piston?
4 inches.
Okay, so the interstage coupler will sit on top of the piston.
Yes, correct.
Okay. And so the thrust transfer at this point,
Wait, why didn't motor up into the upper? Between the two states. Bottom of the I think of the sector.
Sorry, Ben, are you asking us a question, or I can't hear you well, to be honest. Your mic is like really bad in quality. If you want, you can write the question in the chat. I'm not sure if I can hear you well, but if you're not asking us a question, can you mute? Okay, I guess we can continue because I don't think they can hear us.
okay. So from the point of view of thrust transfer,
Yeah.
You would have the booster tube would be pushing directly on the back of the sustainer tube.
Yes.
And also the piston would be pushing on the interstage coupler, which is pushing on the centering ring. Is that also the case?
I mean, technically, yes, but like most of the thrust is going to be from the outer tube. It's not going to be from the coupler.
All right.
Yeah.
Okay. The main concern I have about this is that when the motor lights, if you're doing your hot staging, you're going to that top part of the booster airframe is going to see flame.
Yes.
And then later, that piston tube has to be pushed out of the tube.
Yes.
Okay, so if that tube gets damaged, how is it that the piston's going to make it out of the tube?
Oh, I see what you mean. That's an interesting question. I haven't done any like solid analysis on that, but like since there's going to be more pressure inside, I'm pretty sure any damage will be going outwards, which might I highly doubt it's gonna jam the piston necessarily. But we can do more. We can check that if you want and give like more solid answer.
Okay.
Yeah, because it's like a bomb. I highly doubt there's going to be an implosion. Worst case scenario, it's going to be easier for the drogue to go out than more difficult. At least that's my current assumption.
Okay, well, yeah, I'm gonna have to make a note of that. I think that's something that, I mean, what? Yeah,
I can ask our structural lead and dynamic lead to like do some sort of analysis in terms of that, especially like corrosion in the surface and higher pressure. But yeah, my intuition says that it's not going to be an issue. But yeah, we can check it with math to validate.
If you were to allow it to drag separate, you at least wouldn't damage the piston.
I mean, we can, but like it's too much of change at this point. Like, I don't think we can make that change within a month, especially since most of our tube are already cut to size. Adding more components and stuff, that's probably.
Well, you wouldn't have to add anything to drag separate. You just delay the motor lighting
And
you don't put pins in it. You let it.
oh,
So
interesting.
when the booster cuts out, you wait a second or two, and in that time, as long as your coupler is not too tight, you should drop the booster. Then you light your sustainer. Then you're not at least thrusting into that piston. Your motor's still inside the coupler, which is what I was asking about when this started. But
Mm.
at least you're not losing your drogue.
Actually,
What altitude are
we
you?
don't really. Sorry, we don't really need to change anything because there is already a delay by 2 seconds after burnout. So if we just
You
don't
might
put,
end up with drag separation anyway.
okay, so if we just don't put the shear pins and we like kind of lubricate the thing, it might be enough.
yeah, you 98% of the time, you don't want to shear pin stages together.
Okay. So I guess we don't have a problem then in that case. If we
Well,
just-
you have to examine your simulations to see if the rocket will want to drag separate.
Yes.
And here is a method that you can use.
Mm-hmm.
And what I want you to do is to do this method and then send me the results of your analysis.
Okay.
Okay, and here's the analysis that you need to do.
Okay.
Okay, you're going to have a simulation, and the simulation is going to have an acceleration curve for the rocket, right?
Yes.
So you're going to see the motor acceleration,
Yes.
and then after the motor burns out, the acceleration will go
Yes.
negative, right?
Yes, correct.
Okay, and let's assume that you do not separate the stages at that point. So you have to tell the simulation, don't separate the stages at that point. You want to leave them together for a second or so.
Makes sense.
Okay, and then tell the simulation to separate the stages, but don't light the motor.
Makes sense.
Okay, and now you look at that acceleration curve. If when the sustainer separates, the acceleration goes less negative.
Mm.
Okay, that means that the sustainer has less drag than the stack does.
Makes sense.
Okay.
So if the booster has more drag, that means it will naturally separate.
Well, hypothetically, if if you saw after separation that the acceleration went more negative, then the parts don't want to drag separate.
Makes sense.
Okay, so it's only if the acceleration becomes less negative
Hmm.
that you can say, okay, there's a tendency for the parts to drag separate.
Makes sense.
Okay, and you can imagine that if the booster was really, really heavy,
Mm.
that its momentum is basically pushing the stack, and so there's actually more drag after it separates. You know, I always give an example. Imagine you have a heavy booster like that, and your sustainer is a model rocket. Okay, that model rocket is never going to separate from the top
Yeah,
of it. Okay,
true.
because its momentum is very low relative to the booster.
That's correct.
On the other hand, if your sustainer motor is very heavy and the booster motor burns out, then the sustainer is going to want to separate.
Makes
Okay.
sense.
So what you need to show me is, what does your simulation show when you go through the analysis of the stages separating a second or so after the burnout of the motor?
Makes sense.
And
Yeah,
if
that
it looks
totally.
like it wants to drag separate, then, you know, we just need to make sure that the coupler fits very well. And then it will most likely drag separate.
Okay, that makes sense. Okay,
Okay,
we'll
so
do that. I will send you the results tomorrow. I'll try
do
to.
that analysis, and I mean, you don't have to send it to me tomorrow, but do that analysis and send it to me when you can, that demonstrates that it wants to drag separate.
Okay, we'll do that. That sounds great.
Okay.
Are you using OpenRocket for your analysis?
For basic analysis, yes, but sometimes we do more CFD in ANSYS Fluent if we need more detailed results.
I can't remember where it is, but there's a section in OpenRocket that calculates drag on various components of the rocket, and you may be able to use that information to determine whether you can drag separate or not. I have used it for what size of shear pins I need to use for various things, and that drag analysis is helpful, or that.
Okay.
Yeah, typically when I do this analysis where I look at the simulation curve, I'm typically doing it in RAS arrow. Only because in OpenRocket, they also continue to show the drag of the booster. And sometimes that obscures the results of the simulation.
Yeah.
So
Okay.
it may be that you can arrange that it, you know, that the ongoing acceleration of the booster is not shown on the simulation, because sometimes OpenRocket, it makes it hard to do this particular analysis.
Yeah,
Okay.
I will use that as an estimate to get a feeling of confidence.
Yeah, it really is an approximation, because when the parts are together, and at the moment that they separate, in reality, there isn't the drag separation of the sustainer. So actually, as long as the accelerations before and after separation are pretty close, then it should drag separate.
That makes sense. We will make sure that when we do the analysis that we actually have the right numbers for the right parts.
Yeah, you have to, and yes, okay. Okay, so send that to me, because that's important, because if you're hot staging, you know, there's concerns about toasting and or even blowing up that top part of that booster. Okay?
Makes sense. Makes sense.
And if that happens, then the booster's gonna come in hot.
Makes sense.
That's an important question. You know, it's real important on the safety analysis to make sure that the drogue comes out and you're not
Okay.
coming ballistic. So here we have an issue where it could prevent the drogue from coming out. So this is an important thing. Okay.
Makes sense. We'll make the analysis, make sure all the numbers are for the right parts, and update you with that.
Okay. Then let's go on.
Okay, so we talked about payload quickly. Do you have any questions regarding the payload sections?
Not really. I would just advise you that when you bring the rocket with that clear section, now you're only going to have the nose cone weight above it, but
Yeah.
you know, make sure that someone can't wiggle that or look at that and get concerned about the strength of that tube.
Okay. No, the strength of the tube under compression is actually so the tube itself is 4 inches inside inner diameter and 4.25 outer diameter. So when we put it under a compressive test, like under a hydraulic press, it was actually stronger than the carbon fiber tube. So we are very sure it's gonna survive. Plus, like you said, it's actually the last thing at the top, so it's almost it has the least amount of load compared to the rest of the rocket.
Okay, and in that section of the rocket, so you're gonna have, at the top of your sustainer fin can.
Mm.
There's gonna be, now you're gonna have another airframe for your recovery sections, correct?
Correct.
And what is gonna be the coupler now, let's see, so you're gonna have your recovery airframe and that's going to join to your acrylic tube.
Yes.
Now, is that a separation point?
It is not a separation point, no. Wait, actually, yes, it is a separation point, but the acrylic tube is not a separation point from the nose cone.
Okay, so the acrylic tube and the nose cone are gonna stay together.
Yes.
But you're gonna have a separation point, so what is the coupler going to be at that point? From the
It is
acrylic,
all of our couplers are the same. They are all 8-inch long fiberglass tubes.
okay, so how is that gonna be joined to the acrylic tube? Because the acrylic tube diameter is different, right?
The inner diameter is the same. The outer diameter is not. So for the outer diameter, we're just gonna be using Bondo to make sure that it has like a nice chamfer for like aerodynamics. But other than that, it's the same as any other tube from in the inside.
Okay, and that tube, that coupler tube is going to be glued into the acrylic tube.
Uh, Sorry, can you say that again? I kind of blind.
Which tube does the coupler tube stay with, the acrylic tube or the fiberglass tube?
Oh no, it's gonna stay with a fiberglass tube. So it will be glued to the recovery section and it will just be inserted into the acrylic tube.
Okay, why not do that the other way?
We just want that like because the payload is already like kind of tight in space. We just want to give it like a bit more space to insert things inside.
Okay, you have to insert the payload there.
Yeah.
Okay, again, the issue is you're trying to, put recovery equipment through the smaller coupler tube
Uh,
instead of an airframe tube, so you have
okay.
you have a restriction there.
Yeah, but on the bottom side, the coupler will be on the sustainer tube. That way we can insert the recovery electronics from the bottom. Yeah, so the way the couplers kind of are installed in different sections, they don't follow like one pattern. We just see like whatever works for that section and we kind of install them.
Okay,
So the recovery tubes in our original plan, they never have couplers on both ends. It's always on one end it's glued and on the other end it's glued to the other part. That will always have like enough area to insert anything that we want.
okay, so I'm gonna try one more time. On the center airframe, the fiberglass section, the recovery tube.
Yes.
Is the coupler for that tube glued into the top of the fiberglass tube?
Yes.
Okay, so the bottom of that tube is not going to have the coupler, which
Correct.
means that you're going to have a zipperless coupler.
I don't know what zipperless coupler mean, but I'm gonna assume that.
A zipperless coupler means that you have an airframe tube like the top of your fin can, and then you glue the coupler into the top of the fin can, 4 inches in, 4 inches out.
Mhm.
And you put a bulkhead at the top of that coupler,
Mhm.
and that's your recovery point.
Yeah, pretty much. Yeah, pretty much. I mean, our bulkheads are gonna be a bit lower, but more or less, yeah.
Okay. Yeah, my feeling is that this is not completely worked out yet. So The second assignment that I would give you is to provide a drawing that shows the tubes and the breakpoints.
Okay.
So that we don't have any ambiguity, because right now I think we still got a conflict. So what I want you to do is think about where the couplers are going to go relative to the tubes. And just draw a simple diagram that says which tube the coupler is glued into. It doesn't have to be anything fancy, but let's just make sure we're on the same wavelength.
Okay.
As to
Makes sense.
where the
And I
couplers
will show
are.
you like before and after separation, so like it's kind of clearer where the couplers are at.
Yeah, and then the other piece of data that will probably be helpful with that drawing is from which tubes does recovery equipment emerge from?
You mean when installing and taking them out?
Does it come from the top of that tube or the bottom of that tube?
Okay, I see what you mean. Okay, yeah, we will definitely do that.
Because, yeah, because that's the other thing that's sort of confusing right now as far as
Okay.
where things are located.
Okay. To be honest, we already have the plan and we have it in mind, but we never did a video review before. So I guess it would have been better if we actually had those ahead of time to show it would have been better.
Yeah,
I'll try
I mean, I didn't really provide anybody any instructions for it,
Okay.
but that's why I say it's sort of helpful if you go through you know, the presentation and the report first, and then you can kind of talk about these before you're trying to show airframe sections. You know, it can make it a little bit easier, but we'll get there.
Okay.
Okay, so I think from the point of view of the airframe section, I think I think we've got what we've got at this point.
Yeah, pretty much. I mean, the last part is just the nose cone, which we did the layup yesterday. We still haven't opened the mold, but it's also the same nose cone like our rocket last year, so we know it works. Nothing really different.
Okay.
Cool.
So probably the next most important thing to talk about is the recovery design. So you know, what I'd really like to see is some drawings that show how the recovery system is going to be set up. Did you do anything like that in the report?
Like we have drawing diagrams, like wiring diagrams.
Okay, that's the other thing I kind of wanted to see was the wiring diagram. So maybe, can you call these things up on the computer so we can walk through what the,
Yeah, I can just give me a second. Don't share it. I'm gonna just remove this stuff. Okay, share. Sorry. Yeah, just 1 second. I have the laptop here. I'm just gonna log into my account and get them ready. Oh, I did not. Just 1 second. Sorry about that. I'm looking for the PDF. I love reports. I'm gonna start sharing the screen. Wait a second. How do I enable that? How do I allow sharing the screen? Oh, like I click on a participant and allow them to share the screen. Okay, makes sense. Where are you? Make the host. I'm gonna start sharing. The charge screen share. Okay, so this is our report. Can you see it on the screen?
yeah, are you able to maybe make it a little bit larger?
Yes.
There you go. Okay. What I'm thinking is that, maybe we just start through it from the top, and I suspect there will be pictures and tables and so forth that I have questions about, so we might as well just go from start to finish.
Okay. So, sorry, I zoomed out by mistake. So this report is actually a second revision. So we had like other authors before. So this is the table of content, team history, organization, mission concept of operation, mass budget, aerostructures, extended stress analysis, CFD, propulsion, avionics, and telemetry and recovery. And then we're going to talk a bit about the payloads and the rocket trajectory model. I don't think, do you want to go through the team history and organization?
No, I just want to see the drawings of the rocket for the most part.
Okay.
Yeah.
So this is the concept of operation, the launch, the staging, the separation, and etc.
Okay, let me look at that just real quick.
Okay.
Um, okay, I don't really have any questions about that. Let's just keep going.
Okay. Uh, so this is just like text explanation of what the picture had, so nothing really different. Do you want to go through it or?
No, let's keep going.
Okay. So system over structure, sorry, system architecture overview is just like the rocket itself, a picture from Open Rocket.
Yeah, okay, let's stop there for a second, and let me see if I can see your cursor. Yes, I can. Okay, so start on the left of the drawing there and just point out what each of the internal components is.
Internal, okay. So I'm gonna zoom in. Actually, let me open the Open Rocket. It just might be a bit clearer. Uh, no, I have another one. It just might be easier to see. Okay, so the nose cone, of course, the clear section here. There's the two couplers for it, and here is the payload.
Okay.
And then we have the main parachute. We have main on top and drogue on bottom. Here we have the electronic.
Yeah, I think this has changed from what I saw. But that's okay. I mean, what you have there is the what I would suggest, and then you're going to put out the drogue first. And so where is the tube brake for that?
The tube brake is here at the blue line. So this is the coupler highlighted, and the brake is exactly at the middle.
Okay, and that's the coupler that okay.
And here are the recovery avionics and tracking stuff that goes, and the drogue and the motor retainer and the actual motor.
Oh, okay. So are there some additional descriptions of the recovery configuration, or should we talk about that here?
No, there is in the report. There is in the report.
Okay. Okay, so you have the main chute there, and then you have the drogue there. Okay.
Here's the stage separation. Here's the coupler for between the two stages, and then the drogue with so this is the piston around it, the recovery electronics, main stage, and then the main booster. And overall, that's more or less how it looks like.
Okay.
Mhm.
Another option, I mean, I'll just throw it out and you can consider this. If I had a concern about the drogue coming out of the top because of the staging there,
So you would have a concern regarding what, sorry?
Well, we talked about a possibility that the drogue might not come out if the top of the tube gets damaged,
Yes.
right? Hypothetically, if you put the drogue in the middle and the main on the top, the opening of the drogue would be more reliable.
Oh, like the places?
Yeah, and because that part of the rocket wouldn't get damaged from the hot staging. And
But
say
wouldn't
my main concern from a safety point of view is getting the drogue out.
wouldn't the main be a more important one though, because it actually slows it down to like a safer descent rate?
Not really. I mean, you want them both to come out, but
Yeah.
see if the drogue doesn't come out, the rocket's just going to come back ballistic, and
Yeah.
the main parachute coming out isn't going to help you. It's just going to strip it.
Oh, I see what you mean.
Whereas at least if you put the drogue out first, now at least it's coming down at a speed that's not ballistic. And then you hope to get the main out, but at least the rocket's apart and it's not ballistic anymore.
Uh,
So,
that
you know,
might be doable if so the coupler here, if we make it a little bit smaller, sorry, the bulkhead, if we make it a little bit smaller, that it slides into the coupler, that might be doable, but uh, I don't know, but we said that we're gonna be doing the drag separation instead of hot staging, so
well,
I'll
it's just an insurance if you are able to do it, that it would alleviate any concerns about not being able to get the drogue out.
I see what you
So
mean.
I'm not saying that you have to do it. I'm just offering it as a potential way of making the rocket safer.
Okay. Okay. I'll keep it in mind. After we check the drag separation numbers, if it's kind of concerning, the numbers are concerning, I guess we can just try to switch them for
Okay,
safety.
so let's look at that first. And then, the fallback is reversing the drogue and main so that, that way you can say we're very likely to be able to get the drogue out.
Okay, makes sense.
Let me just make a note here.
Okay.
Okay. So, okay, so now I know where the configuration is. The last open rocket I saw had the drogue and the main chute together. And it looked like it might be sort of it comes out of the same tube. But this version doesn't have that
For the sustainer, right?
for the sustainer.
Yeah, we did change it after your comments because it made sense.
Yeah, I mean, I'm not sure I understood. Well, I'm not sure I understand now if it was intended to be drogue and main out of the same opening or not.
It was not the same opening. They had a bulkhead in between them. But your comment actually made way more sense, so we just changed the design.
Okay, yeah, what you have is okay from a configuration. The challenge that you face with the conventional deployment system is that when the rocket's falling under drogue, the nose cone's pointing straight down. And so now you blow the main out, and it just fouls against the tube because you want them to fly in a V shape under drogue. You know what I mean? You want when a rocket's falling under drogue, the way that you normally want it to fall is in what's called an inverted V.
Yeah.
What looks like this,
Yeah.
coming down like this. The problem is that when you have the heavy payload, instead of being like this, it's like this.
Oh, I see what you mean.
And so then instead of the main opening outward, it opens down and immediately blows back up into the tube it came out of. So that's the design challenge to solve
I see what you mean.
for
This might be a bit too
space.
difficult to change right now.
Yeah, not the, and I'll give you the secret word that fixes this. And you have to go
Actually,
find out.
it might not be too difficult to change. I'll check that.
I'm sorry, I didn't hear you.
I think it might be possible to switch them. I will check that.
Well, you don't want to go drogue over main either. That's even worse.
It's worse? Oh, okay.
Yeah,
Okay.
you know, when you have a payload on a rocket, it makes recovery difficult. And there's no really good way to do it. But when you're using the conventional configuration, main over drogue, the secret to making it work is a deployment bag. And you can Google that and see if you can figure out how to do that. And what the deployment bag does is it keeps the main contained for a few tenths of a second. Till it gets past that airframe and then it pulls the chute out. That's the secret. So, you know, you can take a look at deployment bags and how they're used, and if you can integrate one, you'll greatly increase the chances of getting your main chute out.
Okay, makes sense.
Okay. So I guess let's go back to the report.
Yeah. Just one second. I think I have actually the same. Can you hear me better now?
Yes, you're not echoing now.
Okay, sorry about that. Okay. So we were here. This is some numbers, diameters, lengths, and stuff. Mass budget. This is our centering ring. But oh, by the way, it has a little hole. That way we'll be able to pass down the igniter through a tube. Just makes life easier.
Oh, just the wires.
Yeah, we have a little tube that
I
goes.
see. Okay. Yes.
And what else do we have here? This was an old way. It wasn't an old way. This was our intended way to make the fins through epoxy infusion. But the issue is that the CNC out our school it was broken for a bit, so we just ended up making plates and water jet them. But this way it was amazing. Like we can also put it like on a heater, so it's out of autoclave, and this gave us like amazing performance over years. But yeah, I mean the plates way also works. That's also what we had last year in our rocket. So I just wanted to talk about it because like it's a cool thing we did for a while. Same thing for the sustainer, but same issue. Some stuff, and so that's more of a slightly detailed CAD model. This is how we sectioned it when we put it into the stress analysis software in ANSYS. Load conditions. This was the setup that they used for both structures and flutter analysis. The way they did it is they would do like aerodynamic analysis, and then they pipeline that into the stress, and it got going into circles while increasing the Mach number until we get failure, and that's how we find the flutter speed. And for us, everything passed. It was like 1.4 something, which is exactly our maximum speed. So, and by adding the tip-to-tip layers, it increases the Mach, the flutter Mach number. So everything is okay. More stress analysis stuff. Actually, no, this is flow. This is CFD stuff. So this is our shockwave, how it's gonna look like under maximum Mach, which is 1.4, 1.45, I guess I put. This is the pressure distribution. As you can see, there is a little shockwave here. I don't know if it's very visible on the screen, but this is, again, this is a worst case scenario where the payload section does not have a smooth transition. Everything still works fine with this, but of course we're going to add a smooth transition to have a weaker shockwave. Our motor thrust curve, nothing too interesting. This is a simple CAD of our recovery section for the first stage. So we use featherweight GPS and what's it called? Missile RRC, RRC and RRC3 and Stratologger.
Do you have that built yet?
This
Yes.
we're actually we just finished cutting the bulkhead, so we're gonna assemble it starting tomorrow. We're gonna finish it by next Thursday though.
Okay, so if this is all we can look at, let's spend a minute or so here to
Okay.
look at this design. And so
So this is for the first stage. The second stage has different flight computers. It has Easy Mega and Telemega because they have the tilt lock for
right, okay. So you have an eye bolt at the top between the CO2.
yes.
Okay, and there's a nut on the or a fitting on the back side of that, correct?
Like under it?
Yes.
Yes, of course, yeah.
Okay.
And we usually use lock nuts just to make sure that they don't come off.
Right. And so when the rocket recovers, you're going to have on this one, so you're going to have a drogue on one side and a main on the other, right?
Yeah, sure. Yeah.
Okay. So how does that force? How do you handle the force of those deployments?
How do we handle them? Well, we just make
So
sure that
what holds the two? What is the connection between the two bulkheads?
the connection between the two bulkheads. It is through the plates. It's through the plates and the plates. So the plates are made out of fiberglass, and they are bolted on both ends. So, but also there is really no force that is transferring between the two bulkheads because the bulkheads are screwed from outside to the airframe with 12 eighths of an inch screws. Both of them are screwed, of course. So the force really just goes to the airframe. Nothing goes in here.
Okay, and how many screws was that?
Our stress analysis lead said 12 would be optimal, and he said we can go with 6, but 12 is just better, higher safety factor.
And what size are they?
Eighths of an inch.
Okay, I'm not sure what number that is.
0.125 of an inch.
That's 0.125?
125, yeah.
Oh, okay. I'm not sure what that is, but okay. So you're gonna screw that in both bulkheads from outside.
Yes.
Okay. And I think I see two CO2s and two black powders. So this would be your booster.
Yes.
Okay, and the black powder will be for the main and
Correct.
okay. And okay, let's go on.
Okay. Cool. Um, this is our interface that we use for the featherweight. It just draws a line where it flies, just to make it easier to follow.
Okay, you know, one of the things that I forgot to look at on your progress report number 3 is what tests do you have yet to perform?
Yeah.
Let's make sure we go through that. We don't have to do it right now, but let's make sure when we get done with the report, we go through the list of tests that you're planning to do yet.
Sounds good. Okay. Recovery system. We did some parachute sizing calculation. Nothing too impressive or like important.
And I didn't see descent rates in there.
Uh,
Are they listed somewhere?
where are they listed? The descent rate on the report. Where would you know? Okay, wait, here they are. So let's see, for the booster, I saw something. Okay, According to ensure the team set an objective to descent rate of maximum 20 feet per second at landing. You know, summary. Okay, so this is for the first stage or both? Okay. For both stages, the descent rate anticipated on touchdown is 12 feet per second. 19 feet per second.
Okay. I remember 2 stages had a very high drogue descent rate.
Okay, the numbers that are in Open Rocket are not always correct for some reason. So no, we do our own math to make sure.
Okay, this was in the text that I saw, and I didn't get it from the Open Rocket
Oh,
file.
really?
I got it from text.
Oh, interesting. Wait,
Yeah,
which one?
and I could look it up, but let's.
Oh,
I
it
don't
is,
really
okay.
care what it says there. I care what you think it is now.
Okay, so, I'll let the recovery lead to explain that. Okay, here's the video.
Yeah, so as you can see in the report, the booster stage for when the drogue deploys, its descent rate becomes 68.15 feet per second, and for the sustainer, it's 70.82 feet per second. So, for touchdown, and then for touchdown, where is it? It's 19 feet per second for both of them.
Okay, and how big are those drogue chutes?
They're 24 inches.
Okay, 24-inch, and what style? Are they
They're
elliptical or
elliptical.
toroidal?
They're elliptical drogue chutes that we get from Fruity Shoots, and they're rated for. Fruity Shoots has a descent rate calculator, which we use to determine the descent rates for these.
Okay, those numbers look fine. And they're a lot different than what was in the second progress report. It was like 155 or something.
Yeah.
So, yeah, that looks quite a bit better. One thing to keep in mind when you're looking at these descent rates is that the Fruity Chute descent rate calculator is at sea level. So, and you're actually going to be, I mean, at the point where the drogue is transitioning to the main, you're at nominally 5,000 feet. And so there's a fair amount of difference there. So you should, when you cite the numbers and and do your on-site safety review, you should say something like, here's what the descent rate calculator gave us, and then adjusted for altitude, it's a little bit higher.
Okay.
We will actually check that, and we still have a little bit of money, so if we need to get a bigger parachute, we will be able to.
Well, I think the rates you're talking about are okay. I just want to, just don't be misled by the descent rate calculator, because it's, those numbers are at sea level.
Okay, makes sense.
If you don't end up flipping your bays on your booster, you might want to consider a larger drogue on your booster as well, because it's harder to keep it from becoming ballistic with a smaller chute.
Okay.
Because you're really long. You run the risk of the mass of that booster overwhelming the parachute, and then you'll come in ballistic anyway. So if you reverse it, you're naturally destabilized and you're okay. If you don't reverse it, I would recommend a bigger drogue chute.
Okay, we'll keep that in mind. Here is another CAD of the, I mean, it's a rough CAD, it's not very detailed, but this is the first stage and this is the second stage. It has different, it uses telemega and azimega. And oh yeah, we bought all our batteries are either manufacturer supplied or cylindrical lipos, according to the new rules that were sent.
Okay, so you're getting for the Easy Mega and the Telemega, you're getting the 1S lipos from Altus Metrum.
Is that what we're doing? Yes, that's what we're doing.
And-
Although there is a very slight chance we might switch one of those to the Blue Raven, because some other teams suggested a lot, and we're playing around with it. And we kind of like the interface setup and stuff. There is a chance we might change one of them. But it's also a battery manufacturer supplied battery. But yeah, I just wanted to mention that just in case we end up switching one of the computers. We kind of want to try something new. That's really the only reason.
Okay, yeah, my personal opinion is that like the Easy Mega, Telemega, and the Blue Raven are pretty equivalent. They do have the interface, which is nice for the Blue Raven, but the the thing that's most of the concern to me is the programming for the sustainer igniter. And the programs between the two would be very similar.
No, they will be definitely be similar. Yeah. And here is our first like wiring diagram. By the way, there are two charges for both of them. They are in the same box, but there's actually two charges. So everything is redundant. There is nothing in common between two computers. And I think there's like, how much was it? 1 or 2 seconds delay between them in case. You want to talk more about like recovery stuff? You don't have, okay. But yeah, this is a wiring diagram for the first stage.
Okay, so what is the staging mechanism? Because we've been talking about drag separation. And you haven't mentioned anything about a separation charge or anything. So what is that?
Oh, you mean here? Oh, actually, what is that?
Yes.
Okay, I think that's a mistake from our previous design. Yeah, this should not be here. Because the staging mechanism was the hotspot. Yeah, sorry, this should not be here. Yeah, you can ignore this one.
Okay.
Yeah.
And do you have how are you going to secure those 9-volt batteries?
In the it's not very visible here, but we have like a little plastic like clamp that we actually, can you give it to me? Yeah, we have a little battery. Actually, I can see what the camera is, and we just like kind of secure it. We screw it in, and I think last year it has a cover. Wait, is that the cover for it? No, that's a different cover. But yeah, it also has a cover that comes on top. So yeah.
Okay.
So,
yeah. I'm going to recommend to you that you not use those.
Not? Okay. What? Why?
Because the battery can become separated from those terminals. The terminals don't have a spring loading, so somehow or another you have to force the battery up to the terminals, and under acceleration that can fail. And I'll confess that I lost my L3 rocket because I had battery holders like that. So I have a pet peeve about them. What I would suggest you use instead, what I would suggest you use instead is you just get the little plastic wire connector that connects onto the top of the battery, has the wires coming out of it. Hello, Peter? What I would suggest is you get the little plastic connectors that have the wires that come out of them, and that one thing you can do then is you can wrap electrical tape around the perimeter of the battery over the top of that connector so that it can't come off. Okay. Then when you mount the battery on your board, you use a zip tie both up and down and left and right to hold the battery onto the board.
Okay. We'll do that.
And don't use that battery connector.
Okay, sounds good. We'll do that. Let's see. So yeah, this was a mistake.
Okay.
And that is that's for the second stage. So we have the igniter and the drogue and the main. And I guess we're gonna switch from magnetic switches to key switches, if that's what you recommend. And everything else is also like quite standard, nothing really too crazy.
Okay, now it is a rule that you have to have a switch between the altimeter and the igniter.
Oh, I see. Okay.
Okay, and I suggested that you only use one altimeter for this.
Yes, correct.
And not two. I mean, you can use two if your heart's set on it. But you know, the thing that's important as far as getting the sustainer lit is to have the igniter stay into the motor. It's not the E-matches and it's not the number of altimeters, because if your altimeter is supposed to work 98% of the time, it'll fire the charge to the igniter. Okay, so when you use two altimeters, you might go from 98 to 99.
Mm,
Your chances of failure double, because you have double the chance of inadvertently lighting the sustainer when you don't want to.
I see. Okay.
Okay, so it's
So
false
just use one.
reliability to use two altimeters. Now you can use an igniter that has two E-match heads if you want.
Mm,
That gives you a better chance of lighting the pyrogen or whatever you're using for your igniter. So
okay.
what, you know, that's a very common thing. But the idea is to focus on just one altimeter and doing it safely.
Okay.
Now
We'll do that.
you have to have a switch
Okay. We'll
on
add
the
a switch
way
here.
to the igniter.
We'll
Okay.
add one here, and we will remove then the other igniter.
Right. Now, if you're going to go with the key switches,
Hmm.
right, you can get a double pole, double throw key switch.
So it uses, we can have one switch for both of them?
Well, what you do is you have a switch for both legs of the igniter. But then the other thing that you do is you have the other two legs wired together so that you shunt the igniter when the switch is in the off position.
I'm not sure I understand.
Well, are you familiar with the idea of twisting the igniter leads?
Yeah.
So twisting the igniter leads is another way of saying you're shunting the igniter. Okay, you're just shorting out, you're just making a continuous path of the igniter. So if you can imagine the igniter and you have the circuit is essentially like twisted wires. It comes up to the switch and it goes past that shunt and then back to the igniter. So that's shunting the igniter when the switch is in the off position. And then when the switch is in the on position, it removes the shunt, but connects both legs of the.
Okay. So that way it's impossible to misfire, right?
It makes it more difficult to do that.
Okay,
Yeah,
no, I
I
understand what you
mean,
mean.
the basic rule is you have to disconnect at least one leg to the igniter.
Okay. I see what you
Better
mean.
is separating both legs to the igniter.
Mhm.
And better still is separating both legs and shunting the igniter.
Makes sense.
And if you're
Okay.
using a key switch anyway, you can get them double pole, double throw, so that you can shunt and disconnect. And there's a wiring diagram in the D tag that kind of shows that concept of, how you would use a double throw, double pole switch so that you shunt and then deshunt when you open when you connect the switch.
Okay,
So
makes sense.
if you can do that, if you're using the key switches anyway, that's that will improve your safety to use that kind of a switch.
Okay, makes sense.
And then when you launch the rocket, that switch is the last thing that you connect.
Makes sense.
Okay.
Okay, we wrote that down. Just to make sure I understood correct when you were talking about the batteries, you meant we use those, right?
Yeah, something just like that.
Okay, sounds good.
It's actually, I mean, I prefer to use ones where the wires come out of the top instead of out of the side.
So like it's just easier to. Okay, that makes sense.
Yeah, I mean, that makes it a little easier to wrap the electrical tape around the battery. But you can go the other way around the battery too if you're going to use zip ties.
Okay,
So,
sounds good. Yeah, I
yes,
just
so
wanted to make
yeah,
sure
that's
that
the connection, and then like I say, that you can positively connect that with the electrical tape so that it won't come apart.
Sounds good.
I've just got to pipe up for a second. I've got to drop out. I've got another appointment in half an hour that I have to leave for. So, John, I'm sure I'll stick around, but I have to drop out.
Sounds good. Thank you, Shane, for coming.
Yeah, you bet.
All right, so let's keep going.
Jim, you mentioned about the way they're going to install the igniter in the sustainer motor. Do they have a plan for that?
Our plan was just to put it on a long, like full noodle and just push it all the way inside.
Okay, just want to make sure you don't want it falling down with acceleration.
It's probably gonna burn. Because like it's too light anyways, it's made like a foam and it's probably gonna burn by the time everything is ignited.
No, I don't want the igniter to slide out of position when
okay,
the
okay.
booster ignites.
Okay, now I see what you mean. No, yeah, no, we had that in mind. We had that in mind.
Okay.
All right, so let's talk about that a little bit.
Okay.
So what kind of igniter are you going to use for the sustainer?
They usually supply the igniters with reloads, so we're just gonna be using that.
Okay, yeah, I refer to those igniters as the igniters that you purchase that are already broken. So,
Oh,
you know, the one thing that you know, do you have the motors yet?
yes, we have them. We don't have them here in the workshop, but we bought them since last year.
Okay, well, when will you get possession of them?
We're gonna pick them up like a week before we drive down to the US.
Yeah. Oh, you're not going to try and drive down through the border with them, are you?
We are actually, we checked and it's perfectly fine.
Okay, because
they are not, they're uncontrolled goods, and there was actually a letter for borders specifically for those type of motors that they are okay to transfer, and we asked other Canadian teams and they said they did it. So we from different sources we are quite confident we can take them with us.
Okay, I'd be interested to find out.
Yes. Yeah, one thing I would just suggest is since you're getting the motor a week ahead of time, that you remove the igniter and you inspect them and you make sure that they are not cracked and broken and that you can measure the resistance of them. And you should get, you know, 1 to 2 ohms for resistance and just do an inspection of them because oftentimes they're broken. And I'm going to take about 2 seconds just to check the radar here real quick. These storms are moving in.
Okay.
But I think we're okay for the moment. Okay.
Hope forever.
So one of the things that I want to talk about with you is doing something that I refer to as an all-up test on the sustainer as you're getting ready to load it on the rim. And the concept of an all-up test is that basically you turn everything on and all of the switches and everything just as you're going to do when you're launching the rocket, except that the igniter is not in the rocket at that time.
Okay, cool.
Okay, so there's a couple of things that you can do to make that all-up test easier to do. Yeah, well, let me say first that all-up test is really important because that's the thing that you do where you turn everything on and all the switches are on and you're out there at the pad and you verify that the igniter doesn't fire. Okay, that's your last safety. Okay, so you want to do the all-up test if it's at all feasible to do it. So one of the things that you need to be able to do the all-up test is to be able to pull the igniter out and then put it back in. All right. And And if you're going to use a stick to mount the igniter, like a stick or a little tube or something,
Mhm.
one trick is that when you hook the igniter to that stick or that tube, you just tape it down halfway.
Hmm.
Okay, don't tape the wire all the way down the stick. Just go halfway. And if you do that, then you'll find it's a little bit of an optical illusion, but if you do that, you'll find you can pull the igniter out. Even if there's no slack wiring at the bottom of the motor, you can still pull the igniter out. Okay, so just write that down and prove to yourself that it's really true, because it's not easy to visualize, but it's true, okay?
Okay. And of course, we need that in case we want to scrub the launch, we need to pull it out. That's the main reason.
Well, sure, I mean, yeah, if you had to scrub the launch, you need to be able to pull the igniter out also. But, you know, if you taped the stick all the way down to the bottom of the stick, then you'd need to have a bunch of slack wire in order to pull the igniter out. Okay, you don't want a bunch of slack wire down there in order to be able to do that. You want to be able to pull the igniter out without having a lot of extra wire down there. And if you only tape it halfway down, you can do it. Yeah. Trust me on this and give it a try. You'll just
Okay.
go, oh, cow, he's right. You can pull the igniter out. If I only tape it halfway down, you can pull it out without having a lot of extra slack.
Interesting. Okay. We'll try that.
So that's one way to help you do the all-up test. The other thing to do the all-up test is that you want to be able to have the rocket vertical, because that's how you're going to be launching it. And with the Telemega and the Easy Mega, the rocket has to be vertical when you turn on the altimeters. Otherwise, they boot up in the USB mode, right?
Mm.
When you have the rocket horizontal, they boot up differently than if it's vertical. So when you do the all-up test, it has to be vertical.
Mhm.
So you need to kind of have a way of holding the rocket vertical while you do the test.
Okay.
Okay, and the way I do it is I have like a piece of well, I'll just call it like PVC pipe. Maybe it's a foot long, and maybe it's 6 inches in diameter, and then I can set it in there and I can set it on the fins.
Mm.
And I won't be screwing around with the wires on the bottom of the rocket.
Makes
Okay,
sense.
make sense?
Yeah, makes sense.
Yeah.
We also have a vertical stand for the rocket. One of our members is printing it, so we can also use that maybe.
Yeah. However you want to do it, but you want to be able to set it vertical, and then you turn everything on just like you will when you put it on the rail,
Mhm.
and then you turn everything back off, and you're ready to fly. When you prove to yourself that you don't have some problem with your electronics that would cause the igniter to fire.
Makes sense.
So, and you'll have time at the 2-stage pads to do that. You don't have to rush out like you do at the single-stage pads. You have a little more time that you can wire things and install igniters and do that sort of testing. So incorporate that into your plan, because, you know, as a new 2-stage team, that's a really important test for you to do, is to be able to show right before you fly that you can turn everything on and the igniter's not going to fire.
Sounds good. We wrote that down.
The other thing on the igniter is that you want to hold it into the bottom of the rocket
Mhm.
when it fires. And just to give you an example, and I tell this to all the teams, you know, some teams say, well, all we're going to do is we're going to have the stick in there, and then we're going to put our red cap on the bottom of the nozzle, right?
Mhm.
But the problem is when you just hold the stick in with the red cap, the cap blows off and the igniter spits out. You know, it doesn't hold the igniter, and the secret to getting the igniter to light the motor is to hold the igniter in for just a couple milliseconds so that it can burn while it's still in the right position at the top of the motor.
Yeah.
So what you have to do is you have to figure out some way to hold the stick in that doesn't block the nozzle so the gases can still get past.
Okay.
Because otherwise you'll just you know, puncture, you know, rupture whatever it is you've got. Like if you tape the whole bottom of the nozzle shut, it'll just blow that out and blow the stick out, and it won't light the motor.
Okay.
Okay, so hold the stick in, but don't block the exit for the gases.
Okay.
Okay,
Makes sense.
that's the trick. Okay, so that's what I have to tell you about the igniter. You know, now you're if you're counting on drag separation, you don't have to worry about protecting the wires or the core from a separation charge.
Hmm.
But you do have to hold the stick in so that it will light the motor. Okay. All right.
Makes sense.
So let's continue.
Well, the next section is payload.
Yeah, I don't much care about the payload as long as it's not going to come loose.
Okay, yeah, sounds good. And then, well, more CADs of the payload. Where are we right now? Well, rocket trajectory model. So how each stage is gonna look like more or less. Also quite standard.
There were a few. Go back. There were a few other drawings. There are a few other. Let's back up a little bit.
Oh, and this is for the payload section.
Okay, got it. All right.
It's just like we calculated how much RPM, so we can find out like what's the right motors we need to compensate.
Okay.
And this is the flight path trajectory. If you want to see it more in details, I can open it in OpenRocket.
I'm sorry.
If you want to see it like in more details, I can open it in OpenRocket.
No, let's keep going.
Okay. Some technical risks and stuff.
Now,
Reference.
let me ask you on the payload battery. What are you using for that?
What are you using for payload battery? They're using 2S cylindrical lipos.
Okay, but they're compliant with the battery rules.
Yeah. Yes.
Okay. Let's see. Let me mention so I don't forget it. I sent you an email that had a recommended procedure for programming the altimeter.
Yes.
Have you had a chance to review that yet, or is that down the road a little ways?
I just skimmed over it quickly, but I sent it to our recovery lead. I think he read it.
Okay, well, I'm not going to take time right now to go through that, but what I want you to do is the next step of your assignment to me is to write out a plan for lighting for programming either the Easy Mega or the Telemega. It'd be the same either way. Or if you use the Blue Raven, the same thing. But what I want to see is the timing of the flight, and then how it is that you're going to program the altimeter. So the timing of the flight includes the motor burnout, and then if you wouldn't have a separation charge, so the next thing would be the time that you want the motor to come up to pressure. Okay. So let's say that you said, okay, my motor's going to burn out at 4 seconds, and I want the motor to come up to pressure at 8 seconds or 9 seconds, let's say. And so when I look at your open rocket simulation, I would see the rocket acceleration at 9 seconds. Is for this example. Okay. So then you would back up and you would say, okay, if I want the motor under pressure at 9 seconds, I want the igniter to fire at like 7.5. Okay. So so when there's two things in that write-up that are important. One thing is that you have a relatively narrow window in which the motor can light.
Yes.
So if you wanted the motor the igniter to fire at 7.5 seconds, you might have a T less than 7.6 seconds and a T greater than 7.4 seconds. So just a couple of tenths of a second in there where you've got that window where the igniter can fire. And then at 7, do you have a question?
No.
Okay, so then at 7.6 seconds, that's where you would determine your altitude check value. So you look back at your simulation and you say, okay, at 7.6 seconds, I'm supposed to be at 5,000 feet. And then you would set an altitude permissive that is 70% of the value at that time. So it might be like 4,000 feet, okay? But you determine it at the time, at the longer time in that interval. So from the 7.4 to 7.6, it would be the altitude at the 7.6. That's the altitude check, part of it. So when you send me your program, you're going to give me the timing. You're going to say, okay, here's motor burnout. Here's the lower end of the window. Here's the upper end of the window. Here's where we assume the motor's going to come up to pressure. Then
Makes
how
sense.
did I determine the altitude check value that I'm going to associate with that timing?
Okay.
Okay, and then if you want to, the best thing to do would be then to send me a screenshot of the program that you program if you use the Easy Mega. I don't know if you can do a screenshot for the Blue Raven, but you can for the Easy Mega. And
Okay.
so, if you can send me a screenshot of that program, and it would also need to include one motor burnout. That's a rule in the detail.
Okay. Makes sense.
So what I would suggest is that you stick with the Easy Mega, since you can send me that screenshot.
Okay.
You can show me exactly how you're going to program the altimeter.
Sounds good. We'll do that.
Okay.
Would you consider programming it with a velocity limit?
Generally, I don't. You can.
Yeah, I know I've done that before.
Yeah, the reason that I don't include a velocity typically is that it's kind of like the altitude and the velocity are sort of one and the same. I mean, if you say I have to be at this altitude by this time, then you kind of know what the minimum velocity is at that point.
Yes.
I guess the way I would put it is it's just sort of a redundant check.
Yeah, and I've used the velocity rather than the altitude. Then,
Yeah, except in this case, the altitude is what's required in the detail.
right.
If you want, then I have done it. I mean, you can put in a velocity greater than,
Yeah.
so that you don't inadvertently light it if it's too slow. But if you set up the program the way I've described, you won't be too low on the velocity.
Right. Right.
And I know for sure in the case of this rocket, the velocities are going to be high. One of the problems with the timing of this rocket is that the booster motor takes it to supersonic. So, we're not going to have an issue with the velocity being too low with the particular motors that were selected.
Right.
Makes sense. In terms of the report, I guess we reached the end of the report. So
Okay,
Yeah.
so what I didn't see was a depiction of the recovery approach.
what do you mean by a depiction of the recovery approaches? So I'm sure I understand.
Well, what you typically would do is the best way to do it is to draw a diagram that shows how the rocket will fall under drogue. Not something like a sideways drawing, but actually show drogue and the pieces hanging down, and how far do they hang down, and how long are the shock cords, and what are the fittings along that harness. And a good way to do it is, like I say, draw it just like you think it's actually going to fall. So
Okay.
you don't draw it sideways because it's not going to fall that way. You depict it the way it's actually going to fall.
Makes sense.
And then the next drawing that you show is what does it look like when it's falling under main.
Okay.
And
Makes sense.
those don't have to be anything exotic. I mean, you could draw them out by hand in about 10 minutes.
Okay.
But it's real important to draw that diagram, because then you look at it and you say, oh, gee whiz, when the main comes out, it's going to interfere with this, or my parts are going to hit against each other, or I mean, you actually can visualize what it's going to do when it deploys.
Yeah. Okay. We can also send that in an email. We actually have those drawings like by hand when we were calculating how long we want the shock cord. But you had it, right? Yeah. Okay,
Yeah,
we can send it in
send
an
them. I
email.
mean, it would be, I'd kind of like to see it, because it makes it real clear which tube the recovery is coming out of, and where's the nose cone falling, and you know, it kind of clarifies all of the uncertainties because you haven't given me any drawings that show what the recovery system looks like when it's going to deploy. And that's sort of a requirement for the safety reviews. You got to be able to see what the, you know, how you intend to draw things and how long are the harnesses and where's the drogue connected. You know, all those little details are really important. And so I don't want you to try to reinvent them now, but I would like you to send me a drawing that shows those things.
We'll do that.
And if you can, it actually include the hardware and the ratings of each piece of hardware. You know, what harness are you using, by the way? What style and strength?
So we have the eye nuts. We use eye nuts instead of eye bolts just because it's easier to like attach them. And we
Right.
have the actually, can you give me the box? Where's the box? Where's the box with the parachute and stuff? Yeah. So we're using Kevlar softboard.
Okay, let me just give me a second. I gotta get your, or maybe maybe stop sharing your screen now, and so I can get a
Okay.
larger.
Stop share. Okay.
Yeah.
So
Okay.
it's Kevlar softboards. That's also the same as we used last year.
Okay.
3/8 inch.
Sorry.
Looks like 3/8 inch.
I don't. Let me
Wide.
see what
You don't have to measure it. It's okay.
it is. It doesn't mention. I think it's a 1/4 inch.
Ooh.
But no, it's not a quarter. Actually, I don't remember. I don't remember. Sorry. And we use so we have links that will attach to the eye bolts and sorry, they will attach to swivel links, and the swivel link will attach to an eye bolt or an eye nut. That
the
way,
ratings of all those are important.
yeah. I know the ratings. I just don't have them on top of my head. I can include that in when I send the email. So yeah, we have swivel links and we have the links that attach to them, and then they attach to thing. Yeah, we use swivel links at every place that we might have rotation, so nothing gets too like tight or tension.
Okay. I think that hardware looks okay, and I think the Kevlar looks okay. Do you have any? Are you at the points where you're attaching the drogue and the main? Is the Kevlar knotted, or do you have?
Oh, I see what you mean. Usually at the end of it, we make a loop, and so the loop is like, do you remember I don't have it on top of my head, but let's say it was like an inch loop. We also like stitched it for like another inch or two, with nylon thread, so it doesn't come off. And that's also what we used last year, and it turned out well.
Okay. Why wouldn't you use Kevlar thread for that?
Why wouldn't I use what? Sorry.
The Kevlar thread.
To be honest, it's just what we have in the shop.
Okay, but nylon thread is going to melt eventually.
Well, with your
Sorry.
ejection charges.
Sorry. Can you tell them to just stop for like 15 minutes? Okay. Sorry, someone is like cutting steel, so I have some noise. Can you say that again?
Well, the concern that we have is that nylon can be melted by the ejection charges.
Oh, okay.
So-
Sorry. We also have fire blankets.
No, the thread,
Sorry.
the nylon thread. The
Yeah, but
nylon
like,
thread that you're making the loop of Kevlar can melt.
oh, I see what you mean. Okay, we can buy Kevlar thread. That's not an issue.
Well, let me ask you this. On the Kevlar pieces that you have, do they have loops on the end of them now?
No, they don't.
Okay, so you are gonna sew your own loops on the ends.
Correct.
Okay, yeah, if you do that, then you need to use Kevlar thread.
Okay. We'll do that.
You know, if you told me that I have manufacturer's loops on there on each end, and I'm only gonna use the nylon in something that would be inside of a blanket, then I'd say, well, okay, we could probably accept that. But you're gonna have, your shock cords are gonna be exposed to your black powder ejection charges. And if you use nylon, you're gonna melt that nylon and your loop's gonna come off.
Okay. We assumed it's okay because that's what we used in previous years, but we can just buy Kevlar.
There's always the first time to get burned.
Yeah.
So to speak.
Understand. Yeah, okay, we will get the Kevlar ones. Yeah.
And I'd sew it for at least 2 inches, that loop, that section of sewing on the loop, at least 2 inches.
Yeah, I think that's what we did before. It's just like I don't have it on top of my head. We'll make sure.
Okay, so I think the connections on either side of the harnesses are okay. You'll need to do them in Kevlar. Now, one thing I will just pass along to you is just my personal opinion. And that is I'm a big proponent of using as little hardware as you can on recovery systems. Not so much by the eye bolts, but by the chutes itself, because the hardware is where the harnesses hang up. And so you just get a bunch of tangling if you've got hardware you don't need. I've had a couple people do, you know, level 3 certifications, and they just have all the harnesses are just outfitted with multiple quick links and swivels and this and that and so forth. And by golly, the harnesses fail when they launch the rocket because they just have too many places where it can hang up. So I would do an inspection of the recovery system and say, where do I really need those swivels to be?
Okay.
Just as an example, you might include a swivel for the drogue, but maybe not for the main, because it's not going to be falling under main for very long. So do you really need a swivel at that location? Because if you put a swivel in there, then you need a quick link and another quick link, and now you've got a lot of hardware. So, you know, think about what you really need, and then in your drawing, include the hardware that you decide to use, whatever that is.
Okay. We'll do that.
And as far as the lengths of the harnesses go, you'll probably want for your drogue sections to have not less than 35 feet.
Not less than what, sorry?
Than about 35 feet.
No, 35 feet. Okay.
For the drogue sections.
Okay.
And the reason I say that is, I mean, I might personally use 25 or 30, but you might run into a reviewer that says you need to use 5 times the length of the rocket. This is oftentimes quoted statistic. And so you could look at your rocket and you could say, well, okay, the whole rocket is maybe 15 feet. So I've got an 8-foot booster. So people would say, well, you need a 40-foot drogue section for an 8-foot long rocket. And if you come in with 22, you're probably going to end up walking over to the store to buy, you know, new harness. So you're better off on that one. What I don't want to have happen, if we can avoid it, is you come to the safety review on site and you end up with a bunch of things that you have to go remediate. Okay. And this is a common one. You'll run into reviewers that say, you know, your drogue shock cord is not long enough. And so you end up spending time going off and buying something else, and maybe it doesn't fit, and you know, you have issues. So I'm just forewarning you that you know, you probably need to make sure that the drogue shock cords are not too short, because you'll run into reviewers that object to that.
Okay. Is 3 times the length of the rocket acceptable, or do you think they would ask for more?
Well, for the drogue sections that you're using, you know, I would say on the sustainer, you probably don't want to go less than 30 feet.
30 feet, okay.
On the booster, I probably wouldn't go less than 35.
May I ask why on the booster 35? Because like the drogue is
Well, okay, well, yeah, the reason why depends on the specific configuration that you're using. And in the case of the sustainer, you're gonna with the sustainer, the danger is that you put out the main at apogee.
okay.
And the reason that you might tend to put out the main at apogee is because you've got all the weight of the payload and the nose cone that's being held in by the shear pins
Hmm.
at that point. So when you put out the drogue, now you're using CO2, but you still could potentially get some amount of jerk as when the drogue harness comes to gets pulled out. And so one of the ways that you mitigate the jerk that can tend to give you the main at apogee is to use a longer drogue shock cord.
Mhm.
Okay,
Makes
there's multiple things that you can do. You can size your ejection charges correctly. Use a longer harness. Make sure you have the right number of shear pins for that. So all of that has to be designed. But one important component of that, and particularly for spaceport rockets that have heavy payloads, is to have a longer shock cord for the drogue.
Makes sense.
Now, for the booster, okay, now the booster may be different, okay? So if you put the drogue out as you have it now, out the top, then maybe you don't want to have as long of maybe that one can be shorter.
Okay.
It's kind of hard to say, because if you envision what's going to happen when that drogue comes out, if you have horizontal velocity, you're going to get that drogue is going to try to bend that rocket in half. It's going to try to break the joint down where the main chute is.
Mhm.
Okay, so one of the things that you have to do when you're putting drogue out the top is you have to consider, well, okay, what's going to happen when that drogue chute opens? It's going to go behind the rocket, and then it's going to open, right?
Mm.
And if you have horizontal velocity, one of the things it's going to do is it's going to put a lot of stress on the shock cord at the point where it rubs against the top of the staging coupler, or whatever the coupler is at that point, right? So you need to do things at that point to prevent the tube from zippering or from being, or the harness from being severed.
Mm.
Okay, so I don't know if that affects the length of the drogue, but it does affect the design of the harness that you're using at that point. I mean, you can wrap your harness in masking tape at the point where it rubs over over the tube, so it makes it less likely to sever. That's a common technique.
I see. Okay.
Okay, so that one doesn't have to be 40 feet long. I mean, that one can be 15 or 20. Now, if you put the drogue in the middle, like we were talking about maybe considering, now it has to be longer again.
Mm.
Okay, so, but you don't have as much weight up above it like you do on the sustainer, so maybe it doesn't have to be, I mean, maybe 30 or 35 feet is okay in that position for that one.
Makes sense.
The idea is to go through these concepts and decide, what is it? And that's why it's important to draw out the design so that you can see how's it going to fall, and when the drogue comes out, you visualize when the drogue comes out, how is it going to affect the rocket? How's it going to deploy, and think through those issues. That's real important. I mean, because if you put out the drogue on your booster and you severed the harness at that point, now the rocket's going to come in ballistic, right?
Yes.
So your job from a safety point of view is to prevent that harness from severing. Because it's going to go behind the rocket, and you might have if you're at an angle, you might have 100 feet or 150 foot per second horizontal velocity. You have to prevent that drogue from severing the harness.
Makes
That's
sense.
your challenge. And you know, you can chamfer the tube at that point, so you don't have sharp edges.
Mm,
Okay? You can protect the shock cord, protect the harness at that point, so it's not as easily likely to be severed. Okay?
makes sense.
Those are the things to think about with your recovery design.
Makes sense.
Okay, I'm gonna go down my list here, and see what other comments that we haven't talked about. Okay, you know I'm concerned about the size of the fins. From a
Yes, you
stability
mentioned that, yeah.
point. One of the things that you must be able to do when you get to the competition is prove where the center of gravity is for the booster and the sustainer. And based on not on an open log measurement, but based on an actual measurement with the motors in and so forth, so that you know where the CG is and you know where the CP is, and you can say based on data, this is how many calibers stability that we have.
Yeah, of course. Yeah.
Okay, because you're going to be pretty close, you know, on your stack to being lower than you should be.
Okay.
And because you'll have by far the smallest booster fins at the competition.
Okay.
And so you will need to be able to prove that you have at least 1.5 calibers of stability.
Okay.
You really want to shoot for 2 to 3. Because it's the 1.5 is misleading. You know, it's sort of the rule of thumb. You want to have 1.5 calibers, but really stability is more about the percentage of the length of the rocket. And so when you have a long, skinny rocket, you know, in order to get the same percentage of the airframe length, it's more calibers. So that's why it is on long, skinny 2-stage rockets that you really want 2 to 3 calibers. If you just have 1.5, you know, I mean, I think we can probably launch it, but it may be that you can only launch it when the weather's calm. You know, we don't have any wind, because the thing that happens is as soon as you start getting wobble in the rocket and getting an angle of attack, your stability actually goes down. So, you know, we want to make sure that as best we can that the rocket doesn't wobble when it's starting off the pad. So we're going to want to probably not have a lot of wind, and we're probably going to want to use the longest of whatever rail that is that we have out there, and so forth. But with your rocket in particular, you're going to have to say, okay, we put all of this together and we put all the motors in there and all the recovery stuff. It's just like we're going to fly, and we put this thing on a chair and we balanced it, and here's the center of gravity. Okay.
Okay.
So it's not ambiguous where it's going to fall relative to the CP.
Okay.
You'll also want to now. I'm not sure I asked you, where are your rail buttons going to go on your airframe?
So I know it is not very recommended to have rail buttons on 2 separate sections at the same time. And that's something I want to ask you about. So we were thinking of putting them on our recovery section, since there's like enough space behind them. But I was also thinking of having at least one rail button also on the sustainer. What is your
Well,
recommendation?
let's talk first about the rail button type that you're going to use. So are you planning to use the regular rail buttons?
Yeah.
Round
Just
rail.
the sticker
So
one, yeah.
you have a minimum diameter booster. How are you
Yeah.
going to make sure that those rail buttons are strong enough?
As I said, we were planning on putting them on the recovery section, which has enough space behind it to
Okay,
screw.
but that's going to be way too high on the rocket. You have to have them down at the bottom in order to control the trajectory when the rocket's taken off. You can't have them up on the recovery, because that's 6 feet up in the air at that point.
Yeah. Another way we were thinking about it is we can have a couple layers of carbon fiber that we put them on top of the airframe, and we can just screw through that.
Okay, that's one approach. Now I've certainly seen that done. Now you'd have to do it on each place where you have a rail button.
Yes.
Okay, and it'd probably have to be at least the thickness of the tube, if not twice the thickness of the tube, or you're just not gonna have enough threads in there.
Yeah.
To provide the strength.
Yeah, of course. We were thinking of doing like around like a 1/4 inch thickness.
Okay, and you know, another thing that you consider, which I can't say I recommend it, but I do it myself. And that is to use these I think they call them these PML rail guides. I could probably send you a picture, but they're these plastic guides. They're about 2 inches long, 2.5 inches long, and they have 2 screws on them. And you can use those on minimum diameter because you can glue them to the airframe.
Mm.
And then there's also 2 screws that at least would go through the airframe itself. It gives you a little bit more stability, but mostly you can glue them on. That's where you get the most.
Would glue be enough, or
I'm sorry?
would glue be enough, or should we?
Well, you have to do a good job of gluing it on. I mean, it's a you know it's a surface that would be maybe 1 inch wide by 3 inches long.
Mm.
So, you know, it's a fair amount of surface there that would be glued on.
Okay.
You know, I would say just look at them. They're called PML rail guides. I think they're sold by Lock Precision now.
Okay.
And you know, I hate them because they're very brittle. And it's very easy to break them. You have to be extremely careful using them, but you can use them on minimum diameter.
Okay, we'll check them out.
Okay, and
We actually have a couple of, sorry to interrupt, we have a couple of scrap tubes. We might be able to just like install different rail guiding stuff, and we can just like pull them and see which ones will break at what's like force and see which one is stronger.
Okay, but this is a problem that you have to focus on because if you come in and the rail buttons move at all, you're not going to fly.
Yeah, makes sense.
So you need with the length of the motor that you have, you need to probably have 2 buttons at the locations where your motor is, because the ideal approach is you would have 2 buttons down near the bottom of the rocket that are perhaps 18 inches apart, 18 to 24 inches apart, and then you would have a 3rd rail button higher up on the airframe somewhere.
Okay.
Okay, and so the challenge is to get them all aligned and to be strong enough so that they are not going to break off, and that they pass the safety review. And this is not easy. Don't overlook this because this is not easy. And if rail buttons can move, you're done.
Okay. Sounds good.
I would just recommend that you come in for your on-site safety review with a wiring diagram that is correct. With the changes that we identified, and also showing, you know, which ones are CO2 and which ones are black powder. Okay. And
I'll send you the updated one just to make sure that it's correct.
okay.
Just a question. Are you also going to be our safety reviewer on site, or is that going to be someone else?
I don't know. I have 12 two-stage teams.
Mhm.
And one of the things that I'm recommending that the two-stage teams do is to complete their safety analysis as soon as possible. And let me diverge for a second, and then I'll come back to your question. But one of the things that's going to be important this year, and it's going to be particularly important for you, and that is to fly early in the day. Now, my guess is you're probably not going to be the first ones on the pad. So I wouldn't worry about getting bonus points for flying early. What I would worry about is flying early in the day, whatever day that is.
Okay.
Because last year there was a whole lot of wind, in the afternoon, and we're not going to be able to fly your rocket if there's wind. So if you come in the morning and it takes you 6 hours to prepare your rocket, and you try that on Thursday and you don't make it because of the wind, and then the next day it takes you 6 hours to prepare the rocket, you're not going to make it that day either. So you have to arrange your schedule and your checklists and your timing and your travel plans and so forth so that you can launch in the morning as early as possible.
Makes sense.
And this is going to be really critical this year because there's not going to be rockets launched once the wind velocity comes up. So,
Yeah.
What you need to, now, one thing that they may allow is they may allow a few members of the team to stay out at Spaceport overnight for the two-stage and for the hybrids. And
Interesting.
that gives you an opportunity to get kind of a running start in the morning. And I'm not 100% sure they're going to do that. I think they want to, but I'll let all the teams know if that's something that is going to be allowed. And so you might want to take advantage of that as a way of being prepared. The other way to be prepared is to have a really good checklist so that as you go along, every tool that you need, that you know what it is, and you know that you're going to need this tape, and you know that you're going to need this wrench, and down to the point where it's detailed to that level so that you can make sure you have everything.
Makes sense.
The other thing to avoid is common with student teams is, John has the wrench and Bill has the computer, and oops, Bill's stuck in Las Cruces, so we can't fly. So be careful how you distribute the key components that you need to do the launch. And you don't want to have key components held by 10 team members.
Makes sense.
Figure out how to not have somebody's flat tire derail the launch.
Oh, we had that issue last year. Actually, we made a big list of lessons learned. So yeah, we're trying to mitigate all this stuff after we had some issues with that.
And real important this year, just because of the circumstances. Okay, so make that something that you focus on.
Makes sense.
So getting back to your question, I'll have probably 12 two-stage teams, I think, and a couple of rockets that I'm the flyer of record for. And I'm encouraging all of them to come do their safety reviews early. So I can't do them all. I will try to do as many of the two-stage teams as I can, but there's no guarantee that it's going to be me.
Okay, makes sense. I'll keep that in mind. I actually have a question. I just want to make sure I understand correctly. There was mentioned a couple times that Spaceport is going to be providing tents this year, right? So we don't need to bring any tents with us, right?
I think that's the plan. I think they're going to have probably big circus tents or something that that everyone can go under, and they're not going to be as susceptible to the wind. Now, as I mentioned, you can stay out at the two-stage pads longer than you could at the single-stage pads. So you might want to have a tent to set up out there. Because you could bring a tent and a table and, so that you can do your assembly out there, and you might want to, if you're going to be out there for a couple hours, you might want to have a tent. But in the parking lot area, there's going to be tents.
Okay. And you mean we might be in a couple hours, you mean next to the launch rails, right? So
Yes.
I mean? Okay, I see.
Yeah,
it's
and
like
you might have to leave a time or two if there's another team launching.
yeah.
But you know, with the two stagers, you have to have more time out at the pad because you have to insert igniters and you have to put sections together and you gotta, you know, all that has to be done. So we'll just space the teams out and you can spend more time out there. And like I say, you may have to drop back for launch and then you go back and you continue on with what you're doing.
And how many students would be allowed there? Last year it was like I think 5 for single stagers. Is it more for double?
I would just say try to have as few people as possible.
Okay.
I'm, you know what, you know, that's sort of the secret to safety is you have as few people exposed to hazards and motor igniters and so forth as you can.
Makes
So
sense.
just ask you to think through the plan and say, okay, how many people do we actually need? And kind of minimize it to that.
Okay, sounds good. The only reason I was asking is that last year more than half of our equipment was the tent. So I guess we can just get a smaller tent this year and have more space for equipment. Yeah, I think you answered my question. Thank you so much.
Okay, yeah, I'm just thinking if you're out there for a couple hours, you might want to be out of the sun, you know, that's all.
Okay, makes sense.
But,
Will the
you know,
flyer of record be required to be out at this pad area all the time that the team is there?
I'm not sure, well, I don't know. I mean,
Yeah.
I would typically recommend it.
Yeah, we're sharing a number of teams.
I think he froze.
Yeah.
Okay. But yeah,
John,
John and Shane, and there's a new flyer of record. They are representing all the Canadian teams. So I think there's around like 10 Canadian teams and 3 flyer of record. So they're going to be rotating between us.
yeah, I'm just gonna say the flyer of record should probably be out there when there's things happening with energetics and igniters and that sort of thing.
Makes sense. Yeah.
And the actual loading of the rocket.
Makes sense.
Okay, I think that's all that I have on my list. So I think there's probably 3 or 4 things that you should get to me before too long, because I can't say you passed the safety review until I have a chance to look at all that stuff. And I know you got a lot of work to do, but you know, let's try to get those things to me so that we can make sure we've got a good plan.
Makes sense. Sounds good. We took some notes and we're gonna rewatch the recordings just to make sure we cover everything. And I'll try. Okay, now that there's more stuff, we'll try to like email you maybe end of next week, hopefully. And
Whenever you can, you know, I mean, we know what the issues are.
yes,
You've got a decision point on the drogue on the booster that we've got to look at that. The recovery drawings, I'm more concerned about just making sure that you don't run into some problem at Spaceport. So, you know, I want to see those. I think your connections are okay, but I want to see the links and how it looks when it's deployed. Then we talked about the sections of the rocket, and you should put on there how many shear pins that you're planning to use on each section. And then at some point, you're going to have to do your ground test for the sections too. So you need to show me those when you're done doing those. You'll have to send me those videos. So you got a lot of work to do.
yes.
I'll encourage you to ask questions if you have them. So feel free to do that. And
We'll definitely do.
okay.
Sounds good. We'll definitely email you whenever we're ready. Thank you so much.
All right, you're welcome.
Or I lost power.
Yes, strangely I didn't. We had a pretty good thunderstorm come through, but nothing bad happened, so we're still good. Okay, anything else?
Anyone have questions? No one? Okay, I guess so. We are got. I guess I can do something. Yeah, I don't think anyone has any questions. So we'll email you whenever we have answers for what we've discussed, and should I send the video to you or to who? The recording.
Oh, the recording, there's an Esra email address that you need to find.
Okay.
Send them a link to the recording.
Okay, sounds good.
The questions, you can just send them to me in, the normal email that we've been using. And, make sure to copy everybody, though. Continue to copy everyone as you've been doing.
Okay, sounds great.
All right.
Awesome. Thank you so
Okay.
much.
Thanks for your time. Good luck.
Thank you too. Have a great day.
Bye.